Okay, so this is also an environment for running Python, or which you can use for your machine learning program, or even build an application. This is called PyCharm. I know some of you must have heard it. I have a reason for not using this platform because PyCharm is mainly for development environment. It can also be used to run your program like I'm going to show you now, but it's much more kind of a bit complicated for beginners. So that's why someone who is just starting out this field to use Anaconda, Jupyter Notebook, But PyCharm is also one of the things that, like in our premium course that we're going to start next month, we'll go also, along the way, we're also going to teach people PyCharm, because that is for you to deploy your model. You're going to need, you might need PyCharm or Visual Studio Code, and other environment. But PyCharm is one of my favorite, actually. So now, this thing, what I'm showing you right now, was not built by me. It was built by 3 students who are among you, who are part of our training program. That's the person of Ikeoluwa, Opeyemi Bakari, Ikeoluwa Olorun Toba, and Ogunbi Ishe. These 3 students, they are still university students. In fact, so they are 200 level. So we started a training program before we launched out this course. And these are people, most of them out of these 3 have zero knowledge in machine learning. But within less than 2 months, they've shown great promise. And I made sure they built these alongside with you with no leverage. They started building this a couple of days ago with less supervision from me. And so they developed this module and also deployed it. And I want to show you so that you have an idea of some of the things we plan to do. We plan to teach people in this, even in our premium course, not just to build a model, because as a data scientist, you build a model, but you can also deploy it. When we say deploy it, it's like taking it to the production environment that you can, where the company can, make prediction with it and even make money. That's like your selling environment. So let me show you that. So this is the model they build. Like, you should be familiar with some of the things I'm seeing here, and I import pandas as speeding, non-pi, and all of that. So we only use logistic regression here. Okay, so this is, I'm going to run it. So this, I can walk you through the code, some of which I know you may understand. This first line, they loaded the data. This is the bank's full data that I gave you is in your Canvas dashboard for the project. This second line, what they are trying to do is to encode the categorical variable to make it numbers instead of they are categorical variables, object data. So they are trying to turn it to numbers. Why? In machine learning algorithms mainly worked with numbers instead of characters, letters. So that's what they're trying to do. The target variable, which is the outcome, is labeled Y in your data if you have looked at the data. So they are termed, they have values yes and no. So they are trying to replace it with 1 and 0. Yes means 1, no means 0. That's what they're trying to do. And here, they're trying to bring out your target and the features. Then they split it. I showed you the function of train test split last week. Here, okay, this was the only thing I know that I added, in this code after they supplied with me to scale it, but I know some of them did this also, standardize the data. And then, okay, also this line, this was only my little supervision to change, to vary the values of C. And I'm going to tell you what this line means, what we are going to do today, because we're also doing logistic regression. So here they instantiate the logistic regression algorithm, fit it, and then use it to predict on the test data. All of the other ones, they're only showing the prediction. One thing I didn't show you, which they did a little leverage, I mean, they had to learn this on their own, is to save the model they built with a pickle file, and then they later load the data, load the model to make predictions. So I'm just going to run this on PyCharm. They didn't use PyCharm, but I'm using PyCharm to show you the deployment. So these are let me tell you what these values means, what the result I'm seeing here. This one is what we call the classification report. We just beautify what we call confusion matrix. I'm not going to go into details of that to tell you what precision recall F1 score means for this for now. So, but the main thing I want you to focus on is the accuracy, which is this 90%. So on the model they built, they achieved 90%. But is there overfitting or not? Let's check their prediction. For these two predictions, this is giving us for these two lines here, where the score on test. So the first line, 0.899, is showing their prediction on the test data, 89.9%. And the second one, 89.8%, is on their training set. So that means there is no overfitting. Other ones are just predicting the classes. So let me run this other one. They built this API to deploy the model to see what the output is going to look like in a production environment. So why is this paused? Let me stop sharing. I don't know why it's paused. Let me share again. So can you see this screen now, please? Hello?
Yes, we can see.
Yeah,
Learning machine model.
Exactly. So this was after I clicked, or I actually run it from the PyCharm. This is a deployment environment now, which they built. You can see our company's logo here, machine learning model to identify best model to enhance time deposit. This was the project we gave you. So as if you want to predict now, this can be done if you're working for a customer. This will be the site of a customer. So you are going to deploy it on their website. They deployed it using our website. Okay, so if you click this, you want to make prediction. These were the features that they used after reducing some of the features. So they had to work on the model to see which of the features actually make sense in terms of usefulness to the model. So duration, suppose we have 450 duration, like if you go through the data, you understand what all those features means. Let's say a customer has balance of 200,000, the age, maybe 50 years, and the day 5, the outcome success, maybe 0. Number of days, let's put 20, campaign, maybe 0. Does the customer have house? Yes. And make prediction. And then see, is the customer going to subscribe to a term deposit? Yes. These are the features that I just entered. And you can make you can continue making analysis. So this what we call deployment. So these were done by these young and awesome, training. So when we say that we're going to we want to do a course with remote internship, we meant it. We're not just joking. And this was even done under 5 days. Yeah. So imagine, and this is a project that you can present that, even if you want to launch into this field. So I'm just showing you this to encourage you that you are in the right field. If you will be able to put in the work in a short matter of time, you'll be amazed at what this will bring for you, the kind of opportunity that is going to expose you to, and even bring that you will have. So do not procrastinate, because procrastination kills opportunity, because it makes you assume that you can still do it sometime later on. That's the truth. You will not even recognize the opportunities if you are not ready, if you are not prepared. So I'm going to stop sharing and then we'll start the class for today. So that was just to show you what these couple of students are doing. And these are not even computer science students. So if they can do this, that means you can do it too. Yeah, these are engineering students. At least two of them, when they enter this, I'm not sure they've never even programmed in Python before. Only one of them has, at least an idea. So this doesn't matter. And one thing I love about data science is it doesn't matter your background. Nobody cares if you're coming from economics. Nobody cares if you're not a science student. It is data science is a field that encompasses many fields: physics, computer science, engineering, math, statistics, economics, biology, even any field, as far as you have flair for data, because data is the new oil now. And if you are currently in Nigeria, I mean, some of those in the developer who are among us can testify to this, that America and Europe, they are filled up right now with tech companies. So they are looking into Africa now, actually, to invest this technology. So, but when they come there, who will they meet? That's the truth. Are they going to bring people from here and then be using Nigerians and other Africans to do many jobs? But if they meet people there who are also know, you can be consultants to these companies. You can become partners with them to train people. So, I mean, amazing opportunities for you right there. With this, I just believe that this training can serve as a kind of a platform that you can build upon. This doesn't matter whether you take our other courses, it doesn't matter. That's the truth. Whether you take it or not, this is an opportunity for you to build capacity on. In short time, you will reap the dividend if you will put in the work. Okay, so that is that about that. Let's start the final piece. Where is my notebook? I don't know, when I start to share, it's kind of pause. I don't know why it's pausing. Can you see my notebook, please?
Yes. Yes,
Oh,
sir.
yeah, so this is machine learning tool, and it's going to be short, like I said. So what we want to do today is just logistic regression, because logistic regression is one powerful model out there, whether you're in the e-commerce, is a machine learning algorithm that is very, very powerful. There are many, but we've only been able to introduce it to two. The first one was K-nearest neighbor, and these which is also a classification model, and then the logistic regression. So the question is, what is logistic regression? You have heard about linear regression. There is a reason why I didn't touch linear regression. That's because the model the project was based on a classification problem. So I felt that showing you what you will need for the project is actually the goal of this training, not just teach you something you will not use at that present time. So linear regression is also a linear model, but is used to predict or to model a problem that involves you predicting continuous value. But logistic regression is a linear model which you use for classification. Mainly, it is used to model binary classification. When I mean binary classification, just like what you're working on, like predicting a yes or no question, yes or no outcome, or benign, whether a cancer is benign or malignant or something like that. Just two categories. But can it also be used for multiple? Yes, it can be used to predict more than one class. So you can use it to predict more than one class. We also have other algorithms like the random forest classifier and all of that. But I mean, that's not the goal to get there this, because once you can understand the basics of machine learning and also scikit-learn, all the other algorithms are there. You can play around them. You just need to understand the results you are getting. So this is this equation is similar to that of linear regression. You see y hat, the hat on it shows that is a predicted value. That's what you are predicting. You see some of this is W, one is X. This is the X are the input, the features that you are feeding your algorithm. The W represent the weights or the coefficient in mathematical terms, coefficients of your model, but in data science we call them weights, parameters of your model, because those parameters are actually what your algorithm is learning. Is actually learning the correct value to that these weights are, because the higher these weights, the more your model will overfit. So when I'm going to introduce you to what we call regularization later today, what that regularization is doing when you are trying to regularize your model is to restrict or to push the values of these weights, these W's, the coefficient of the input towards zero. Not all of them, but the coefficient of those features that are not important to, for your model. That's what that regulation is doing. But your general algorithm is kind of trying to find the appropriate values of this coefficient, this W, that is needed for your prediction, to get the accurate prediction. Okay? So your logistic regression, just one thing I want you to take out of it is that it's a linear model that is used for classification problem, that is used to predict the classes or the categories of your output. And I kind of put the strengths there, that one thing is that linear logistic regression or linear models are very powerful on high dimension data set. By high dimension, I mean data with many features, not many rows, many columns. The columns are your features. That's the dimension of your data. The rows are just the samples, okay? So I kind of put here that why the name of learning, when we say machine learning, I explain it here, that the learning is, by learning, our algorithm is trying to learn the overall layout of the classes, the categories, and then find accurate weights, these W's, this coefficient of your input, find the accurate weight and bias, this offset B, to use to build your model in order to reduce the rate at which our model misclassify the data point. In other words, our algorithm is trying to find the appropriate values for this coefficient, this W, to use to build the model so as to reduce the error. Error, that's the difference between what your model is predicting and what it should be predicting. Okay? So, however, in machine learning, you might not really see, for technical reasons, it's not possible to adjust the weight and the bias. But in deep learning, you will see that it is actually. So what can you do to reduce overfitting? Since in machine learning, for some technical reason, you may not be able to adjust this weight. So one solution is what we call regularization. And regularization refers to the process of restricting your parameters, the parameters of the algorithm, to a specific value, mainly to zero, in order to prevent overfitting. In other words, these weights, they are attached to each input, each feature in your data. So the algorithms are built such that they have an understanding of the features that may not be important in building our model. So the regularization parameter in your model can restrict, can push the coefficient, this W, of the feature that is not so important. It will push them to zero. What does that mean if you push them to zero? The idea in your model is that the smaller the values of this coefficient, the lesser the importance of that feature. In other words, if this coefficient, this W, is very close to 0 is a signal to tell you that that feature that has this coefficient close to 0 is not so important. So that's what the regularization will do. So for the logistic regression that we are using, the main parameter that determines the strength of that regularization is C. You will see it in your model. I will show you that. So I say higher values correspond to less regularization, meaning if you use higher value of C, it means that you are not really regularizing your model and it may overfit, but you have to experiment with it. But lower values actually applies more regularization, meaning it may prevent your model from overfitting. So some of the things, so I want to use the load breast cancer, which you used during the exercise last week, but you built K-nearest neighbor algorithm. But let's try this same data with logistic regression. So the first thing I'm trying to get the data here from scikit-learn data sets, import load breast cancer. So let's instantiate it. Let's load the data, cancer, load breast cancer. Okay, we can check the content of this load breast cancer with keys, okay? Just to see the content of your data. So we have the data there, we have the target names. If you want to read more about it, use this, just apply this description on it. These are the feature names. We can check the dimension of the main data there, okay? So we can see that we have 569 rows and 30 columns, meaning 30 features. You can also check other some of these stuff. So let's check the target names in our cancer data. Target is what you are trying to predict. So you can see you have just two classes, 0 and 1, 0 and 1. You can check the target names also to see. So we have the malignant and benign. I know some of you did this last class. So let's split the data. Some of these code there, you can see they are the same thing. The main process is the same thing. The only thing that differs is the model you want to build. But all the other processes of checking your data, the target, they are the same for every data you're going to be working with. Okay, so from scikit-learn model selection, you can press this, a tab can show you what we have. Model selection, import, train test split. So let's instantiate the split function by, we want to split that into the X train, S test, Y train, and Y test. So we have the train text split. So we're going to split the cancer data into S train and S test. We'll split the cancer target into Y train and Y test. Let's say I just want to leave it at 70 because by default, train test split will split your data into 75 and 25%. So let's say I want to leave it that way. And then remember to specify the random seed, the seed. This is just to ensure reproducibility, meaning every time if you specify the random seed, any value, I like using 0, it doesn't have to be 0. Anytime you specify that parameter, it means that every time you run this code again, you are going to get the same data. And once the same data is used for your model, obviously you get the same result. It's a good practice so that you don't get different result every time. So we can check the dimension of the data we just split. Let's check that of the training and the test to just see what we have. So what is the problem? Can I import? Oh, I think I made a mistake.
Your spelling.
Thank you. So this is, so in splitting that, we can see we want to build the model with 426, and then we want to test with 143. The data I gave you for the project was over 45,000. So, I mean, you splitting splitting your data may not really be an issue. So suppose our data, we have done the cleaning, we have done all other stuff like visualizing and all of the other rest. We just want to, we now understand that data. Now we want to build the model. Remember, like I told you, you will not just quickly start with building your model, but this is assuming you've done all the exploration, you've visualized, you've removed missing values if you have missing values, or you have filled the missing values. So now you want to build your model, you've cleaned your data. So the logistic regression is inside the linear model estimator. So from scikit-learn, linear model, we can import what? So there are several other ones, elasticnet and all of the rest. So we want to use the logistic regression, okay? So let's instantiate it. Let me say, use the variable logreg. You can use any other variable name, okay? Logistic regression, instantiate that. I'm going to use the default parameters for now, and then I will work on it, okay? So let's fit the model, logreg, fit it to our training data and our test data. Oh, sorry, Y-train. Okay, and then we can check the accuracy. Accuracy here is another way of checking the loss of your data, because the error, I mean, which is also the loss function, because the lower the error, the more accuracy you are going to get. So if your accuracy is low, it's indirectly telling you that your model is not doing well. So that means the error that your model is making is large, is high. Okay, so to check accuracy, we use the score function like this, log reg dot score on your, let's say we want to do that for the training. So let me wrap that under the print, just to print it, because I want to do for the testing too. So let's put this as train accuracy. Okay, and let's put a space for it to print that. I want just the three significant 3 decimal places. So format, just to format it and make it beautiful, okay? So let me copy this code and use it also for testing. I want to see the accuracy on both the training and the testing, okay? So let's make this on test. Okay, and then Y test. And then see, although I have the accuracy, training accuracy is 94.6, test accuracy is 95.1. Our model did not overfit, but look at this, what you have here, the warning. It's telling you that convergence warning. This parameter is in the solver parameter. It says it failed to converge. Why? The total number of iteration reached limit. So it's telling you that you either increase the number of iteration or you scale the data. Remember I told you, it is a good practice to normalize your data. These are just 500 and something data. And it's telling us that you not normalizing your data is going to be a problem. So that's why it's a good practice as a data scientist to always normalize your data. By normalizing, let me remind you what that means. It means that you want to bring your data to the same scale. You want to make all of the features the same scale, because if the features in your data are in different scales, it has a way of affecting your model. That's the truth, because it will have greater influence on your model. So let's normalize that. So there are many scaling factors, scaling functions in your scikit-learn pre-processing module. But I love using standard scaler because it scale your model to, it scale each features in your data to have a mean value of 0 and a variance or standard deviation of 1. So I'm using standard scalar. So instantiate it, scalar, to be this standard scalar. So let's instantiate that. So you normalize that by, let's save it back as our S train. I want to scale the training and the testing. Okay, scalar. So you call on fit transform on your training, the transform word. You are transforming the training S train, but on your testing, you only call transform. You don't fit and transform the testing. You only do that on the training. So on the test data, let's call it S train scaled and S test scaled. Okay, scalar. So we only call the transform on the test data. Okay, then we can instantiate the model again. Let's still use the default parameters. By default parameters, I'm not changing anything. These are the hyperparameters. I'm not changing any of these parameters. I'm still using a C value by default. The C, the regularization parameter I talked about earlier, is 1. Let's still use it. Penalty, these two main factors, penalty and C, are what actually regularize your model. Let's still leave them as this and see the effect, okay, on your model. Let's use the default parameter. So we instantiate it here, then we fit it again, okay, on the scaled version now, S-train scaled, and then we can check the accuracy. Let me just copy this code here. Just check the accuracy again. So, but I'm going to use the scaled data. Okay, and then we can run it. See, it didn't give us those warning again, but now our model overfits. Train accuracy is now 99%, and test accuracy is 95.8. Still higher a little bit than the previous one, but it's now overfitting seriously now. Let me remind you what overfitting means. It means that your model performed very well on the training data, and then it couldn't generalize well on the testing data. That means that your model, your algorithm, is actually memorizing the patterns in the training, but it's too weak to understand the patterns in the testing. So what is the solution? Let's quickly visualize the accuracy using different values of C. Remember, I showed you that by default, the C parameter here is 1. So what if we use C, values of C less than 1? Remember I said earlier that lower values of C means more regularization. So so here I want to visualize the accuracy using lower values of C less than 1. So I tried this, you can try other ones too. So this code here, you should be familiar with it because we use this kind of code last class to visualize the accuracies for the different values of the parameter we're interested in. So let me just run this. You can see that for all the values I actually supplied, my model overfits from the very beginning. So that means no matter the values of C, this regularization parameter C that I supply is still going to overfit. There might be one of these might be, my data is small, so maybe I need more data. 2 is that the penalty, remember I told you 2 parameters that are very important for this logistic regression, the C and the penalty. By default, the penalty is L2. I won't go deep into what L2 means, but some of you who have mathematics background can remember what we call L2 norm, L1 norm, and all that. They are distance actually parameter. So, but in the light of machine learning, penalty L2 norm can be similar to what we call ridge regression. I won't go deep into this, like I said, but these are things you will get to understand more if we have more time. And what L2 normally, what it does is that it pushes this coefficient that I showed you earlier, this weight parameter, it pushes them nearly close to zero. Yeah, but not exactly zero. It pushes them close to zero so that's not all the weight, but the weight of the feature that the model feeds is not so important. So it pushes them close to zero so that they have minimum or less impact on our model. But if we change the penalty term to L1, we can also use L1, which you will see now. We'll try that. What that L1 does is that it actually pushes the coefficient to exactly zero. L2 push the coefficient to close to zero to minimize the impact of those coefficients that are not so important. But L1, in terms of regression, we call it lasso regression. They push the coefficient of our input of the features that are not important to exactly zero. They make them zero, meaning that they are saying that those features are not important for building our model and we are not going to use those features. Turning them to exactly zero means that your model did not use those features. In other words, lasso regression or L1 penalty, they are used for model selection, feature selection, to select the most important features. So we are going to try that now and so we'll use this same code, but now we're going to use the penalty term to be L1. So let me just copy all of this same code. Let me just copy all of this and paste it here. However, I observe, okay, let me show you. Let me allow you to see that yourself. Penalty L1. So I'm going to run it, and I'm sure it's not going to run. And I will tell you why. Because it says that this solver parameter LBFGS supports only L2, none or non-penalties, but I supplied L1. So what's the solution? If I use, it's talking about this solver parameter, this parameter here. You see the default is LBFGS, but it doesn't support the L1 penalty. So what's the solution? We can change this solver parameter to, there are a couple of them, but I'm going to use the linear. Yeah, you don't need to bother yourself about what all of these means, okay? So let's use this. I believe this should support the L1. Okay, you can see. Now I have the accuracy for the different values of C and these hyperparameters, penalty of L1. Now, you can see there is a point here where the test accuracy and the training accuracy are actually the same. They got the same value. So this looks like maybe 0.15 or thereabout. So let's try now and fit the model using that value, maybe 0.1 or 0.15. Let's try it, because that's the point where there is no overfitting in our data. After that point, you can see the training accuracy becomes more higher than our testing accuracy. So the point of doing this is to try to know the exact parameter to use to build your best model. That's why we are doing this, visualizing all of that, so as now to use the parameters we can see from the visualization to now build the model. Okay, so let me use 0.15. I don't know, maybe I'm correct based on this, and then fit the model and then check the accuracy again. So let's see. You can see I got it based on, so I saw that from this. So you can see that the training accuracy has been reduced from 0.991 to 0.971. And our testing accuracy actually jumped up from 0.958 to 95.8, now to 97.9. So this is one tactic. I'm just trying to show you the different techniques to build good model, because your model needs to be good in order to predict. Okay, so before your model can be very good, before you can take it to the deployment that I showed you earlier before we started this class, you have to try the different techniques. In real world, we will not only use logistic regression. Like this student I told you, they explore different models. They explore random forest, they explored logistic, k-nearest neighbor, before coming out picking logistic regression as the best model. So that's the same way. You're going to try different. And you are going to try that in today's exercise. At least you tried logistic regression and k-nearest neighbor. So this is what we're able to give you. So in order to summarize everything you've learned so far, first, we started with data cleaning, removing missing values, exploring your data, visualizing your data. That is what you normally start with. This is the final aspect where after your model, your data are now in the ready state, you're now going to start building your model. But even in the process of building your model, you have to try out several algorithms. But the first question you always need to start with, if you are given a problem, is this a machine learning problem? How do you know if it's a machine learning problem? Do we need to build, is there something we're trying to predict that we cannot do normally, as a human? If the answer is yes, then that is a machine learning problem. Then the next thing, is it a classification problem or a regression problem? How do you know that? Are we predicting not values like house price, the price of a good, all of that? If that is it, then that will be regression. But if it is, are we predicting whether, categories, or whether, someone is going to get approval, yes or no, or we want to predict categories of a particular product, then that will be classification. Then the next thing is get your data. Is my data in the right format? 99% of the time, that's going to be no. So what can I do? You have to clean the data. Do we have missing values there? Try to understand the data, explore the data, visualize it to check the relationship between some of those variables. After you do that, then you convert some categorical features to numeric features, just to have an idea, just to get your data in a ready format, because your machine learning algorithm will not use categorical features, they use numbers. Okay, and then you can start trying out the several classification algorithms like k-nearest neighbor, logistic regression, random forest, support vector machine, extreme gradient boost, and so many, naive Bayes. I mean, those are just names. You can read about them. That's the truth. So and then you normalize your data. It's a good practice to split your data so that what the data you use to build is not the same data you're going to use to test, something like that. And then you try to regularize it if it's overfit, and then come out with your best model. So I am going to stop sharing now to take one or two questions before we go to the breakout rooms, so that we can finish up this training. Okay.
Yeah, so I have a question, sir.
Yeah, let me pause.